Assalamu alaikum. My name is Mubin Malik and today we are going to implement multiplexers or MUXs for short in the Verilog HDL. So this is what a basic 4-to-1 multiplexer looks like. Now the purpose of a multiplexer is to give selected outputs for the given inputs. So these four are the given inputs and these are the controls for the selected outputs. Now as there are two controls, so there are four total combinations possible, each combination for this one input, which means if one of the combination is applied, one of these inputs will be shown at the output. So for the first implementation, this is the code and this is called the gate level implementation. This code works by declaring the gates, what their inputs are and what their outputs are. So here is my implementation. This is the actual code. So and this is the RTL diagram. You can see that these AND gates are controlled by these control inputs, and these are the actual inputs that are to be displayed at the output. Now this is the simulation which I will explain to you that how these multiplexers actually work. So the first combination in which the control 1 and control 2 both are 0 lies in this region, and for that the output is declared by this input 1, which means when the control 1 and control 2 are 0, the output we get is the input 1. Now for the next combination, when control 2 is 1 and the control 1 is 0, the output we are getting is following input 2. This input 2 is mirrored at the output. For the next combination, control 1 is 1 and control 2 is 0, and the input which this output follows is input 3. Same goes here when both the controls are 1 and the output follows the input 4. This is basically how the MUXs work. The next implementation is the logic statement implementation. This implementation, basically, if I show it from my code, is just assigning the output what the logical value of the output will be. So if we see from the RTL diagram, the logical output will be an AND of these three, or the AND of these three, or the AND of these three, or the AND of these three. And this is the collective OR, and this will be used to give out the output. This is the same waveform which we will obtain from this implementation, and you can see this is how I have implemented the inputs and used them as a logic build-up for this output. The next implementation or the method is the case implementation. The case implementation works by declaring two variables which are the control variables and assigning them 4 values, and for each one value we have to declare the value of output. We have to declare what the value of output will be. So for the value of 0 0, which means when control 1 and control 2 is 0, the output will be IN or input 1. Let me show you from my code. This is the code. When the input is at the control 1 is 0 and at the control 2 is 1, the output is input 2, and so on. This is the case implementation, and it will have the same waveform as the previous cases. The next case is the assign method. The next example is the assign method, in which the values are assigned in the form of bits. This is the select, which means this is the control system or the control lines which is a 2-bit system which has 4 combinations, and D is a 4-bit system which represents the 4-bit input. The Q is a wire, and which is basically the output, and we are assigning the value of Q as D of select, which means the D will have the value depending upon the combination of the select. And this is the same code just written in the Verilog HDL, and this is its MUX diagram basically, and this is the same implementation all the way from. So you can see here the select inputs or the control lines are displayed here, and these are the actual inputs that are to be displayed at the output. So if we see where the both select lines are 0, the output is following the first input or D0. For the next case where the select line 2 is 1 and select line 1 is 0, the output is following the next input, which is D1, and so on. For the next case, D2 is being followed, and for the next case and the final case, D3 is being followed. This pattern is repeated in this implementation right here, where if statements are being used. If statements simply define that if the value of the select is 0 or the first combination is selected, D gives out the Q follows D0. If select is the combination 1, Q follows the input D1. If select input is second combination, Q follows the input D2, and so on till the D3. And for the last, this is the conditional statement where a condition is applied, which is basically if-else statement but in a different form, where and represent if and this colon represent if then, which means if select is 0, then D is 0. If select is 1, then D is 1. And if select 2, D 2. And in any other case, if for any select value for which 3 only remains, the value of Q will be D3. The waveform is the same for all these outputs. Now for the assignment part, we have to write and simulate the Verilog codes for a 1 to 4 line demultiplexer, which is essentially the opposite of a multiplexer, using the gate level, logic statement, case statement, and if statement method. So if I show you my code, this is the code of the DEMUX with the gate method. As I have described before, gates are displayed right here. The NOT gates, AND gates, and there is no OR gate in this case because only one input is being displayed at the output. I will show you how through this diagram. Now we only have the one main input, and B and C are the control lines. Now what the demultiplexer does is that it uses these control lines or selection lines to control at which output the value of A will be displayed. So as there are 4 possible combinations, so for each combinations the value of A will be displayed at a different output. This is the waveform which will be used to explain the function of DEMUX to you. So this is the first selection line, this is the second selection line, this is our main input which is to be displayed at the output. Now for the first combination, when B and C are 0, the value of A is displayed at the output W, or the first output. The W follows for the interval where B and C are 0. Now for the next part where C is 1 and B is 0, A is displayed at the second output X. Same goes for the part when the B is 1 and C is 0, A is displayed at Y, and where both of B and C are 1, the A is displayed at Z, and the cycle repeats itself. This is the logic level implementation of the same DEMUX, and you can see for the first output it is assigned the value of A and not of B and not of C. You can see from this diagram that the first W is A and not of B and not of C. Same goes for X, Y, and Z, and this is basically how the logic level implementation works. And it will have the same output because the functionality of DEMUX does not change with the inputs, or how the inputs are actually given, or how the code is written. This is the RTL of the DEMUX through the logic, and this is the same waveform. You can see that for the value of B and C at 0, A is displayed at W. For C at 1, B at 0, A is displayed at X. For the next step at Y, and for the next step and the very last step at Z. This is the case study or the case implementation for the same DEMUX. And now how this works is that for the cases of for the combinations of B and C, the value of W is A for this combination, the value is X, value of X is A for this combination, value of A is at Y for this combination, and value of Z is equal to A at this combination. Again, the waveform remains the same. There is no change in that. And this is the RTL diagram. This is the last if statement of the DEMUXes, and you can see the procedure is just same, only the difference is of the syntax. And how this works is if the selection, now the selection is an input with two bits, and it has 4 combinations. So for the first combination, the value of A is at W. For the second combination, the value of A is at X. For the third combination, the value of A is at Y. And for the fourth combination, the value of A is at Z. The waveform, this is the RTL diagram, and this is the waveform for the if statement or the if implementation of the DEMUX. This was our assignment, and thank you very much. Allah Hafiz.